Hello everyone, let's do tutorial number 6. So tutorial number 6, so we should do practice over sets and relations, okay? So question number 1, we have a set A, which contains 2 elements, 1 and 2, and a set B, which contains 3 elements, A, B, C. Would like first to calculate the Cartesian product A times B. So as usually, so the Cartesian product is that it's equal to the set of tuples. So pair every single element from set A with the element in set B. So I'm gonna pair element 1 with A as a tuple, element 1 with B, element 1 with C, and the second one, element 2 with A again, element 2 with B, and element 2 with C. And be careful يا شباب, because A Cartesian product with B is not equal to B Cartesian product with A. Here I start with the elements from A paired with the elements from B. But here I need to start with element from B paired with element from A, like here, for example. Would like to do B Cartesian product with A. So I'm gonna start with element from B, which is A. I'm gonna pair it with the elements that exist inside the set A, which is A with 1 and A with 2, and do the same with the other elements coming from B, set B. So B with 1, B with 2, and C with 1 and C with 2. So the number of elements generated inside the set is still the same, but the value, the order differs according to which set is written first and which set is written after that, okay? So the Cartesian product of A, Cartesian product A, which means I'm gonna do the Cartesian product between A and itself. So set of pairs, one paired with itself, and one paired with 2, and 2 paired with 1, and 2 paired with 2. Okay, Shabab? Okay, great. So this was question number 1. Question number 2 is, okay, it's asking me about the cardinality of the Cartesian product. So if you're gonna do a Cartesian product between set A that has M elements and set B that has N elements, the Cartesian product will have N times M elements, يا شباب, okay? Like here, for example, A, the cardinality for A was 2, and the cardinality for B was 3. So the cardinality for the Cartesian product, it will be 2 times 3, which gives 6 elements here. Here, for example, the cardinality for A is 2. So the Cartesian product, A times A generates a cardinality of 4 يا شباب, okay? 4 elements. Okay, great. Question number 3. List the ordered pairs in the relation R from set A, so this is the domain, to set B, this is a codomain, where A comma P belongs to R if and only if it satisfies the following conditions. So the first relation, I want to add the pair, the tuples, in which element A is equal to element B. Okay, Shabab? Okay. So I'm gonna pair 0 with 0, and 1 with 1, and 2 with 2, and 3 with 3. So here I'm gonna pair 0 with 0, 1 with 1, 2 with 2, and 3 with 3. And if you notice here, you cannot pair 4 with any other value here because there is no 4 in set B. Okay, so this is the first relation that satisfies this condition, the equality condition. The second condition is that element coming from set A, which is A small, less than the element coming from set B, which is B small. So yes, I'm gonna pair 0 with, I cannot pair 0 with 0. I can pair 0 with 1, and 0 with 2, and 0 with 3. And now I can pair 1 with 2 because 1 is smaller than 2, and 1 with 3 from here. And I can also pair 2 from set A with 3 from set B. And that's it. Okay, Shabab? Okay. So the third relation is that the value coming from set A added with the value coming from set B, the result should be 4. Okay, this is okay. Can I pair 0 with anything from set B in order to have a result of 4? No, I can't, because the maximum value, the highest value here is 3. So I can pair 1 with 3. And I also can pair 2 with 2. And also I can do addition between 3 and 1. And of course, I can add also 4 coming from set A with 0 coming from set B. So the sum A plus B always 4, ya shabab, which satisfy the condition written in part C. Okay? Great. So question number 4. Question number 4 is very easy. We have a relation R1 and relation R2, and I'm telling you that those two relations on the set 0, 1, 2, 3, 4. Can you find the union between the relation? If you notice here, ya shabab, the relation is just a set, which means set operations can be applied over the relations. So relation R1 union with relation R2, it's the set that contain the union between all the values inside the two sets. So without repetition, 0, 1, 1, 2, 2, 3, and 2, 3 is already repeated here. I don't have to write it again, and 3, 4. Okay, so this is the union. Can you do the intersection? Yeah, of course. The common values between the two relations. What are the common tuples between the two relations? The tuple, the pair 2, 3. Can you do R1 minus R2? Yes, of course, R1 minus R2. It means all R1 without the common, without the intersection between them, which is the set of tuple 0, 1 and 1, 2. Can you do R2 minus R1? Yes, of course. All R2 without the intersection, which is, okay, a tuple of 3, 4. Okay? Great. Okay, so let's move to question number 5. Question number 5, the given is a relation R. So this is given. And relation R is on set A. Okay, why not? Would like to find the inverse for the relation. So the inverse is very simple, as we explained in the lecture. So reverse of the relation is all the tuples, but in reversed order. So I'm gonna swap the two elements of every tuple. So A with A again, and here B with A, B goes to A, and here B goes to B, and here C goes to B, and here C goes to C. Okay, Shabab? This is great. And this is how we do it when we list the tuples, but also in order to do it from the graph representation, this is question number 6. Let R be a relation on set A. Can you explain, and if R is being represented as a directed graph, can you explain how you get the inverse R? Yes, of course. So the inverse R is that if I have, like for example here, A, B, C, A, B, C. And I'm gonna demonstrate it on question number 5. And goes to A, B, C again. And here A to A and A to B and B to B and B to C and C to C. So this is R, ya shabab, okay? Can you do R inverse? Yes, of course, I can. It's okay, but I will try to write this down at the left. A, B, C, and A, B, C, which is that one. I'm gonna do it on the right. And now every arrow do its opposite, okay, Shabab? For every arrow, go and draw its opposite. So I'm gonna draw an opposite arrow from A to A, from B to A, from B to B, from C to B, from C to C. So this is the Shabab, how you get the inverse relation from a directed graph representation, okay? So to obtain the graph of R inverse, it's sufficient to reverse the arrow in the graph representing R, ya Shabab, okay? This is good. Question 7. And question 7 is that, okay, if this is a relation on a set 1, 2, 3, can you represent this relation as a matrix? Yes, of course, I can. So here, a relation on a set, it means it will be a square relation. So because here I have 3 elements, so it will be a dimension of 3 times 3, 3 rows, 3 columns. I'm gonna list 1, 2, 3 here as rows, 1, 2, 3 as column. And for every pair, if it exists, I'm gonna represent the intersection as 1. If it doesn't exist, I'm gonna represent the intersection as 0. So 1 map to 1, okay? This one exists. 1 map to 2, 1 map to 3. And there is no tuple of 2, 1. 2, 2 doesn't exist. 2, 3 doesn't exist. 3, 1 doesn't exist. 3, 2 doesn't exist. 3, 3 doesn't exist. So this is M. So also, can you do the R inverse from the matrix representation? It's okay. Instead of having 1 goes to 2, it will be 2 goes to 1. So this is actually finding the transpose of the matrix that represents a relation R. And the transpose is that you're gonna convert every row to be a column. So first row will be first column, second row will be second column, third row will be third column. And this is how we represent the inverse of a relation in the matrix representation, if the original relation is given as a matrix. Okay. So now let's go to question number 9. Question number 9 is given set A, set B, set C, and knowing that this is a relation R1 that relates set A to set B, and relation R2 that relates set B to set C. Can you do composition between R1 and R2? R2 composite R1. It means I'm gonna start with R1 and try to find out A goes to B from R1, followed by B goes to C from R2, and I'm gonna combine the two together and start with A and end with C, and that's it. So A goes to B and B goes to C, so I'm gonna represent an equivalent path directly from A to C. So how can we do it? It's very easy. Let's practice. Try to search. Okay, here A with 1. Is there anything that starts with 1 in relation R2? Yes, there is. So it will make me go directly from A to X. Okay, Shabab? Is there any other pair that starts with 1? No. So let's check the second pair in R1. A with 2. Is there any pair here that starts with 2? Yes, there is. 2, Y. So combining A with 2 and 2 with Y will give you 8 goes to Y. And doing the same process again, combining B with 3. Sorry, here I don't have anything start with 3, but I missed to combine A with 2 with another value, which is 2 comma Z. So the composition generates 8 goes to Z. Okay, Shabab? So here is the composition R2 composite R1. Okay? Great. Question number 10. Question number 10 is that consider the relation R, which is this one, on set A 1, 2, 3, 4. Can you find its inverse? Yes, of course. The inverse is very easy. We said the inverse is that I'm gonna swap the two elements, every two elements inside the pair. So 3 was 1, and here it will be 4 goes to 1, and here 2 goes to 3, and here 3 goes to 3, and here 4 goes to 3. This is okay. So can you do a composition R composite itself? Yes, of course. R composite itself. So I'm gonna check 1 with 3. Is there any other pair that starts with 3? Yes, there is, which is this one, 3 with 2. So combining those together, it means that I'm gonna get the pair 1, 1, 2. Okay, great. And again, 1, 3, and 3, 3. So the result is 1, 3. So, okay. And again, 1, 3, and 3, 4. So the result will be 1, 4. Okay. So I've finished the first item. Take the second item and try to do the same operation. 1, 4. Is there anything that starts with 4 here in order to combine with? No. Okay, skip it. 3, 2. Is there anything that starts with 2? No, there is no. Okay, why not? 3, 3. Is there anything that starts with 3? Yes. Okay. And what is that one? It's okay, with itself, it generates 3, 3, and with 3, 2, it generates 3, 2, and with 3, 4, it generates 3, 4. Okay, Shabab? So those are all the elements inside the composition of R with itself. And as I said يا شباب, الcomposition سهل أوي إنك تعمله من الجراف. It would be great to do it from the graph, okay? How we do it from the graph? It's very easy. Draw 1, 2, 3, 4. 1, 2, 3, 4. And try to represent the R on the graph, which is okay, we can do it. 1 goes to 3, 1 goes to 4, and 3 goes to 2, and 3 goes to 3, and 3 goes to 4. So now I represented R واحدة بس. Go and represent another R. 1, 2, 3, 4. But make sure to have a common set between الاثنين, okay? So another R عشان أنا عايز أعمل composition between R and itself. 1, 2, 3, and 1, 2, 4, and 3 to 2, and 3 to 3, and 3 to 4. And try to draw هنا استخدام اللون الأحمر مثلا. 1 goes to 3 to 2. So here I have 1 to 2. 1 goes to 3 to 3. So here I have 1 to 3. So 1 goes to 4 and 4 goes to nowhere, so it doesn't count. بعد كده let's do it بالأصفر. 3 goes to 2 وبعد كده 2 ما بتروحش مكان تاني، لا خلاص. 3 goes to 3 and 3 to 2, so it goes 3 to 2. 3 goes to 3 and 3 to 3, so starting is 3 and end is 3. And so on يا شباب, okay? So this is how we do it. Okay, great. So, can you do a composition between R and R inverse? Yes. And a composition between R inverse and R. Be careful يا شباب, because R1 composite R2 is not equal to R2 composite R1. Okay? Be careful. هنشوف مين هنبدأ بيه الأول. Given دلوقتي R inverse and this is R, can we do this one? Yes, I'm gonna look in the element coming from R inverse first, followed by the element coming from R. Okay? So 3, 1, is there anything that starts with 1? Yes, there is. So here it generates 3, 3. 3, 1, followed by 1, 4, so it generates 3, 4. 3, 1, is there anything that starts with 1? No. Again, 4, 1 with 1, 3. So this is 4, 3. 4, 1 with 1, 4. This is 4, 4. Is there anything here that starts with 1 to combine with? No. So let's do the same process with 2, 3. 2, 3 combined with 3, 2. So it gives 2, 2. And 2, 3 combined with 3, 3. So it gives 2, 3. And 2, 3 combined with 3, 4. It gives 2, 4. And again, here, 3, 3 combined with 3, 2. So it gives 3, 2. 3, 3 combined with 3, 3. It gives 3, 3, but it's already listed before. You don't have to count it again. 3, 3 with 3, 4. It gives 3, 4, and I don't have to write it again. It's there. So 4, 3 with 3, 2, which is, okay, let's remove the highlighter here. 4, 3 with 3, 2. So this is 4, 2. 4, 3 with 3, 3. So this is 4, 3. Does it exist? It exists. Yeah, I don't have to repeat it. 4, 4. 4, 3 with 3, 4. This is 4, 4. I don't have to repeat it. Be careful يا شباب. هنا I have repeated elements, so this doesn't count. Like for example, here 4, 3, you don't have to repeat it again. So this is the correct answer. And if we do R inverse composite R, so it means that I'm gonna start with R followed by R inverse. So 1, 3, is there anything here that starts with 3? Yes, there is. 1, 3 with 3, 1, it gives 1, 1. 1, 3 with 3, 3, it gives 1, 3. And do the same with 1, 4. 1, 4 with 4, 1, it gives 1, 1. I don't have to write it again. 1, 4 with 4, 3, so it gives 1, 3. It's already there. 3, 2 with 2, 3, it gives 3, 3. Okay. 3, 3 with 3, 1, it gives 3, 1. 3, 3 with 3, 3 gives 3, 3 again. Okay. 3, 4 with 4, 3 gives 3, 3 again. So this is the result. Okay. Very good. Let's go to question number 11. Question number 11 is that, okay, how many relations are there on the set B? How أنا بجيب relation is that? How can I get a relation? A relation is, it could be done in two steps. First of all, find the Cartesian product between A and B, or A with itself if it's a relation on a set like this. And after that, find the power set of the result. So this is, it gives you all the possible relations يا شباب عندنا. So here, set A contains 3 elements. So the Cartesian product between A and itself, it gives you 2 to the power of 3. Okay, شباب? Okay. This is okay. And here, you'd like to have the power set of it. So this is 2 to the power of elements اللي كانت هنا. Again يا شباب هنا, step number 1 is to find the Cartesian product between الست ونفسها. Here I have 3 elements with 3 elements, which means in elements, عدد elements inside the Cartesian product is 3 times 3, which is 9. And step number 2 is to find the power set of the Cartesian product is to find out all the possible relations, which means the number of possible relations that could be generated is 2 to the power of number of elements, which is 2 to the power of 9. Okay, let's do the same on a set that contains 4 elements. So first of all, Cartesian product, and the cardinality for it is that number of elements 4 times number of elements 4, so you have 16 elements. In order to have all the possible relations that could be generated from 16 elements, is that this is 2 to the power of 16, because this is the number, the cardinality for the the power set يا شباب. Okay, sorry. So question 12. Let R be a relation on a set A with m n elements. If there are k non-zero entries in the matrix representing R, which means فيها k pairs, how many non-zero entries are there in the matrix representing R minus 1? Like the same number. Because we know that the difference between R and R minus 1 is that if there exists a pair here, A goes to B, the same pair exists, but in a reverse manner, B goes to A. So if we have here K pairs, also here I need to have K pairs. Okay, Shabab? Okay. Given the directed graph representation for two relations, how can the directed graph of the union, intersection, difference, and composition of these two relations could be found with example? It's okay. For the union, ya shabab, it means add all the passes together from the first and the second, ignoring the repetition for, of course. And for the intersection, I'm gonna add only the pairs, the arrows that corresponds to the pairs that are common between the two relations. And for the difference, I'm gonna remove the commonality from the one I need to do it. And for the composition, if, for example, 1 goes to A and A goes to M, I'm gonna represent an equivalent one goes to M directly instead of having those two, okay? You can practice more by having examples. So let's do question number 14. Question number 14, which is the following relations on the set A, which is A, B, C, D, are reflexive, symmetric, and transitive. So now I have A, B, C, D. This is my domain. So I have A to itself, B to itself, C to itself, D to itself. So of course it is reflective. Symmetric and transitive, we already know how to find symmetric and transitive, how to check it. For symmetric, if you have A comma B belongs to R, so B comma A should belong to R. So, Shabab, is there any two values here? A goes to B, where the first one and the second one are different? No. So I failed to find the left side. If the left side is false in the implication is true. So which means this is symmetric. And as I said in the lecture, if you fail to find the condition for the implication, so the implication is true. It's not violated, Shabab, okay? Okay, great. And let's do transitivity. Transitivity, it means if A, B belongs to R and B, C belongs to R also, so A, C belongs to R also. So this is if else also. If you have a transition from A to B and from B to C, if you have such two transitions like this, so the shortcut A goes to C should exist also. But here, if you have a look, the condition is not available. So which means the left side is false for the implication. If the left side is false for the implication is true, which means it's transitive. Okay. Here again, relation 2. A goes to A, B goes to B, C goes to C, D goes to D. So every element goes to itself. So this is reflexive. And A goes to B. Do I have B goes to A? No. So it's not symmetric. So here A goes to B and B goes to C. I already have A goes to C. Yeah, so this is transitive يا شباب. Okay, great. Let's practice more. Here I have A goes to B, B goes to C. I don't have A to itself, or B to itself, or C to itself, or D to itself. So it's fair enough to say this is not reflexive. And if I have A to B, do I have B to A? No. So it's not symmetric. Sorry, this is a mistake. And I already have A to B and B to C, but I don't have A to C. This doesn't exist. So it's not transitive. So I'm gonna correct this. This is not symmetric. Okay, great. So last one, the empty set, the empty relation. The empty relation is not reflexive because I need to have A to itself, or B to itself, or C to itself, or D to itself. And because no, those pairs are not there, it's not reflexive. But it is symmetric because I will fail to find the left side of the implication. And if the left side of the implication is false, so the overall is true. So it is symmetric. And the same for transitivity. I will fail to find the left side for the implication condition for the transitivity. If the left side is false, the implication overall is true, which means that this is transitive. Okay, Shabab? Very good. So let's do question number 15. Question number 15 is that, okay, given this set, find relation R on A which is not reflexive, symmetric, and transitive. Not reflexive, okay, great. Miss to add, don't add at least one of those, 0 or 0, and 1 was 1, and 2 was 2. Missing one of those three elements will make the relation not reflexive. So I'm gonna add 0 with 0. I'm gonna miss 1 with 1, for example, and 1 with 2. It doesn't matter. Only one of those makes the relation not reflexive. And symmetric, it means, okay, if you have 0 with 1, you have also 1 with 0. Okay? And transitive, so here, like for example, I'm gonna remove this one in order to be transitive, sorry. So this relation is not reflexive, but symmetric and transitive. Because here, 0 is 1 and 1 is 0, it gives 0 is 0, which already exists, okay? Okay, but if you see this one, it's not transitive because 0 is 1 exists and 1 is 2 exists. So the transitivity, in order to be transitive, I need to have 0 is 2, which is not there. If you need to keep all of those, add 0 is 2 and again. But be careful, if you add 0 is 2, you need to add 2 0 in order to keep the symmetric. يا شباب, okay? So I'm gonna remove this one and that's it. ماشي? Very good. We need to find one which is reflexive, but reflexive it means I'm gonna add 0 with 0 and 1 with 1 and 2 with 2. But neither symmetric nor transitive. It's okay. You can add 1 with 2 without adding 2 to 1. And you can add 0 with 1 without adding 1 with 0. And now 0 with 1, 1 with 2. I need to add 0 with 2 in order to be transitive, but I don't want to convert it to transitive relation, يا شباب, okay? So like, for example, such an example like this. Okay? Let's check whether this answer is correct or not. So I need to have those, and 0 with 1 and 1 with 2. Yeah, it's the same answer as the one I just raised. So symmetric, but neither reflexive nor transitive. Okay. Symmetric, so add 0 to 1 and 1 to 0, and 0 to itself without adding 1 to itself, and also without adding 2 to itself. Okay. So here, why this one is not transitive? Because, like, for example, here, ya shabab, I have 1 goes to 0 and 0 goes to 1. I need to have 1 to 1, but when I removed it, it makes the relation not transitive. Okay, shabab? So here, transitive, but neither reflexive nor symmetric. Okay, 0 to 1 and 1 to 2 and 0 to 2. This one. Reflexive, okay, I need to have 0 to itself, 1 to itself, 2 to itself. Symmetric, but not transitive. So 0 to 1, 1 to 0. 1 to 2, 2 to 0. But here, it's not transitive because I have 0 to 1 and I have 1 to 2, but I don't have 0 to 2. I don't have it, which makes the relation not transitive. Okay, great. Reflexive, transitive, but not symmetric. Reflexive, I need to have every element to itself. Transitive, okay, I need to have 0 to 1 and 1 to 2 and 0 to 2, but I don't have the other way, 1 to 0 and 2 to 1 and 0 to 2 and 2 to 0. Okay, shabab? Okay. And again, all of those are similar. So let's go to question number 16. Question number 16, I already have set A, which is 0, 1, 2. Find the relation R on A, which is symmetric and anti-symmetric at the same time. So the empty set is the empty relation is symmetric and anti-symmetric at the same time, because you're gonna fail to find the left side for the implication for both the two conditions, which means that the implication is true. And also here, 0 is 0, or 1 was 1, or 1 was 1 and 2 was 2. The condition for symmetric is that if you have this part belong to the relation, the reverse one also belongs to the relation, where A and B are not the same. Okay, so you're gonna fail to find the left side, as I said, which means that the implication is true. And the anti-symmetric, its condition is that A comma B belongs to R if and B comma A belongs to R when A is equal to B. Also, you don't have this but in the condition for the implication doesn't exist, which is okay, which makes the implication is always true. Neither symmetric nor anti-symmetric, so this is okay. I'm gonna say I have a relation from 0 to 1 and from 1 to 2. If it's like this is anti-symmetric, but it's not symmetric because I don't have the other way going back from 2 to 1 and from 1 to 0. in order to violate also the anti-symmetric, I need to add, like, for example, here, 1 goes to 0. So the condition for anti-symmetric is that you have all the directions, all the transitions in one direction. You can have the other direction goes back. So because this one exists here, it's not anti-symmetric, and because the other way here is missing, it's also not symmetric, okay? Great. Question number 17. How many anti-symmetric relations are on the set that contain only one element? So if the set that contain only one element, like for example, this one, in order to find all the number of relations, not the anti-symmetric, try to figure out how many relations exist. So I'm gonna do the Cartesian product. So here, one element times one element, which is also one element. So it contains A, comma A. So the power set of it contains the empty set and A, comma A. Okay, Shabab? So this set is anti-symmetric, yes, and this set is also anti-symmetric. We just mentioned it في السؤال اللي قبل كده. So I have two relations which are anti-symmetric relations. What about if you have set of two elements? So like, for example, set of two elements, and to find the Cartesian product between A with itself, so you're gonna have 4 elements, and to find the power set of the Cartesian product, it will be, يا شباب, 16 elements. So 16 different relations, but how many of those are anti-symmetric? It's very easy, يا شباب. So the main issue here is that, okay, if you have A goes to B, you don't have to add B goes to A. Okay? Which means, يا شباب, don't go to list all the relations for the 4 combinations. So I'm gonna do it step by step. Again, back here. If I have set A, which is A, comma B, A Cartesian product with A, it's A with A with B with A, B with B. If you go to find how many possible relations can be generated from this Cartesian product, you're gonna say the power set of this amount, which generates 16, okay? But I don't want to have those 2 elements together, because if you have the one and its backward direction, the relation wouldn't be anti-symmetric anymore. So what I'm gonna do is a little bit, it's just a trick. I'm gonna keep only one of the 2. I don't care which one I'm gonna keep it. It doesn't matter, because I care only about how many عدد elements, okay, شباب? So I'm gonna keep only 3 elements, and I will remove the one which makes the problem for me for anti-symmetric. So here, how many elements exist? Which is 3. Okay, شباب? Okay. So those 3, combine it with the how many, wait a little bit in order to declare it. So يا شباب دلوقتي, as I said, I'm gonna keep واحدة بس منهم, هسيب ال A, B وهحذف ال B, A عشان الاتنين ما ينفعش يبقوا موجودين مع بعض. So دلوقتي, how many possible relation could be generated from this form? 2 to the power of 3, which is 8. Is it all? لا لسه. And actually, if I remove the two tuples A, B, and B, A, still I have anti-symmetric relation يا شباب برضو. So added with, how many possible relation can be generated from the set that contains the two tuples A, comma A, B, comma B, which is 2 to the power of 2, which is 4. So the overall is 12 يا شباب. And in order to find it out, there is a form you can substitute directly to find out how many anti-symmetric relation. أنا كاتبها لك أهو. لو عندي عدد elements, number of elements is 1. So how many possible anti-symmetric relation? 2 to the power of 1 times 3 to the power of 1 times n minus 1, which is 0, by 2. 3 to the power of 0 is 1. So I'm going to have here 2, and the correct answer was 2, which is correct. And here, if I have two elements, n is equal to 2. So 2 to the power of 2, which is 4, times 3 to the power of 2 times 1 by 2. So this is 4 times 3, which is 12. Same answer, we got it. Okay. So you can even memorize the relation or the form for finding out how many anti-symmetric relation could be generated from a set. Or يا شباب, you can do it the same way as I've done it, applicable. Okay. So question number 18. Question number 18, find reflexive closure of relation R. But relation R works on a set of 0 and 1. Reflexive closure, it means I need to have every single element mapped to itself. So I have here 0, I need to add with I'm gonna keep the two elements and add extra, which makes that the new relation is reflexive. I'm gonna add 0 goes to 0 and 1 goes to 1. Okay, here I have 0 to 0, 0 to 1, 1 to 0, 1 to 1. So the reflexive closure is still the same, يا شباب, because this is reflexive. I don't have to add any new items. Okay, find symmetric closure. Symmetric closure is, okay, if you have A goes to B, make sure to have B goes to A. If you don't have it, just add it. I have 0 to 0. 1 goes to 0, so I need to add 0 goes to 1. Okay. So I have here 0 goes to 0, 1 to 1, and 0 goes to 1, and 1 goes to 0. So this is already symmetric, so you don't have to add more. So the symmetric closure is the same as the given relationship. Last question is that, okay, can you use the Warshall method in order to find out the transitive closure of this relation? Yes, of course. So first step, draw the relation. So I'm gonna draw the relation, which is here. Okay. Okay, great. And the Warshall method says that, okay, go to every single node. I'm gonna start, check at node A. Count how many ingoing arrows, how many? 1. How many outgoing arrows? 2. So you need to draw equivalent of 1 times 2, the number of ingoing arrows times the number of outgoing arrows, shortcuts. Those shortcuts should be using A to move from a place to another place. So how many potential shortcuts should I draw now to يا شباب? And what are those? Like, for example, C uses A in order to go to D. So this is the first shortcut I'm gonna do it from C to D directly. And also C uses A to go to B. So this is the second shortcut I'm gonna use it now. So the new graph would be this one. And now go and process the second node, which is node B, and do the same scenario again and again and again. How many incoming arrows here at node B? 2. How many outgoing arrows at node B, which is 1? So the potential shortcuts I'm looking for is equivalent of 2. Those shortcuts should be using node B to reach from a place to another place. Yes. So first, A goes to B to C. So I'm going to shortcut A to C directly, which is this one. And again, from this graph, C goes to B and goes to itself again. So I'm going to shortcut C to itself. So now I already drawn the two equivalent shortcuts I'm looking for. So go and check at node C and do the same again and again. At node C, how many incoming arrows? At node C, this is 1. And be careful, ya shabab, because this one is counted twice. This is a loop back. It's counted as outgoing and also incoming arrow, okay? So here is 1, 2, 3. I'm gonna add this. And how many outgoing arrows? Here 1, 2. Sorry, مش 3 يا شباب، أنا آسف. تعال نعد تاني. How many incoming arrow? Let's use blue. This is 1, 2. Okay. 3, 4. So I'm gonna look at 4. And how many outgoing arrows? أعملها بالأخضر. Here is 1. Here is 2. Here is 3. And الخارجة بتاع دي 4. 4 times 4. So I'm looking for a potential of 16. This is the maximum I can do, يا شباب, okay? But you can do less, of course. In order يا شباب to get the exact number of shortcuts I need to add, don't count a loop back دي, okay? Don't count a loop back in order to get the exact number يا شباب, okay? So let's count again without the loop back. How many out? So this is 1, 2, 3, out 3. How many in going arrow? This is 1, 2, 3. So I'm expecting to add 9. Those 9 transitions should be using C to go from a place to another place. So, Shabab, B to itself, this is number 1. And A to itself, this is number 2. And again, back. Let's do again and again. Okay. And A to D. Okay. It's already there. You don't have to write it. And B to D. Okay. And E to D. Yes. And now A to D. It's there. Okay. E to A to B. Sorry, to D. You can write it also. So I'm gonna have all the possibilities, like for example here, E to B. So you draw it also. Like for example here, B to A. Okay, شباب. So after figuring out all the shortcuts, so this should be transitive, and this is the end of our tutorial, شباب. Thank you very much and good luck.